Good morning, everyone, and thanks for those of you who are sticking with us until the very end. So for the final talk of our final day, Hugo will continue with the final lecture of the series. Yeah, Hugo, please.
Thank you very much. Thank you for coming back today. Yeah, so what I'm going to do today is try to give you a little bit of a direction map on the proof of what of the four-dimensional result. And what I put here on the board is what we finished with yesterday, which was this improved tree bound. So we had this tree bound, which was bounding the Ursel four-point function by this diagrammatic sum, meaning that I'm summing on y and I'm summing the spin-spin correlation with the 4 points. And we saw that in a dimension larger than 4 strictly, then it's sufficient to imply the triviality, the fact that U4 is much smaller than sigma x1 up to sigma x4. But that it was not sufficient in 4D because you were getting something on the same order. So what I did here is that I improved by putting this bubble, and notice here that in 4D, so when eta was anyway strictly larger than 0, so remember that we have this scaling hypothesis, when eta was larger than 0, even the normal tree bound was sufficient. But now if eta equals 0, then BL of beta C, which is the sum of the square of the spin-spin correlation for the point in the box, then this will be in fact logarithmic. It's really off-order logarithm. Thus, you get that U4 is smaller than 1 over, is a big O, of 1 over L to the 2D minus 2. This is what you would get for sigma x, for the correlation between sigma x1 and sigma x4. Sigma x1 and sigma x4. But I get this additional log L to the C. So that concludes the proof. Under the scaling hypothesis, you have to trust me that you don't need the scaling hypothesis, in fact, if you get this improved tree bound. So what I will do today is to try to explain to you why you have this improved tree bound. Okay, so let's define T, and this is going to be a key player. It's a random variable, it's a set. So T is going to be the intersection of the cluster in N1 of N plus N2 of X1 with the cluster in N3 plus N4 of X3. And remember that basically we had that U4 is equal, is bounded by twice sigma x1, sigma x2, sigma x3, sigma x4. And here we had this probability when I was sampling 4 currents. Probability that T was non-zero, was non-empty, right? I was looking at the probability that all the points are connected, which exactly means that they are non-empty. Don't hesitate to interrupt me if something is not clear in my writing. In particular, maybe to lighten a little bit the notation, I would just write this as P, X1, X2, empty set, X3, X4, empty set, okay? Just to lighten the notation. So this is what we had. We had probability, we were sampling this, yeah. Yeah, exactly, yeah, sorry. This I should definitely, so C n of x is by definition the connected component of x in n hat. Right, n hat is a percolation where you have edges that are open if if it's 1 and closed if it's 0. So I look at the connected component of the point x. Thank you very much, because this is an important point for, I mean, you cannot understand the next things if you don't understand. Okay, sorry. So very good. And here, what we did before is that we just bounded this probability of intersection we just bounded it by the expectation of t, the cardinality. I'm not re-putting here. And that was sufficient in higher dimension, but notice that if you do that in our dimension 4, then you get order 1, and this explains why you don't get anything. So now we are going to use we are going to use random walks interpretation to try to understand how we may improve on that. So if you take a random walk, you take 4 points, 2 random walks. You take 4 points at generic distance, meaning that they are at the same distance of each other, let's say L. Then in 4D, we have exactly the same phenomenon that if you look at 2 random walks that are conditioned to go from x1 to x2 and x3 to x4, the expected number of intersections is 1. But notice the following observation is that if now you put x1 and x3 close to each other, let's say even neighbors or same neighbors, and you keep x3 and x4 like that, and you do the same game. So you may think that because they have a tendency not to intersect here, maybe there they have positive probability of not intersecting. Of course, it's not probability tending to 0, they are close to each other. But it's not the case. What happens here, and this is kind of easy to see using a second moment method, is that if I take an annulus, but not a dyadic one, I take k and k to some power larger than 1. 1 plus c, let's say square, for instance, k squared. Then the probability of intersection of the 2 random walks is positive on this annulus. Let me explain to you why. Here I told you the expected number of intersection is 1. Now, if you just look at the number of intersection and you look at the second moment, you will agree with me that just using the green function estimates, you will actually express fairly easily what the second moment is. Just go look at, at what you get, and you get something logarithmic. Why? Because you are going to sum G0x squared on every x. And this is going to give you something logarithmic, every x up to a scale which is comparable to the scale of the distance between. So you get a second moment which is logarithmic, a first moment which is of order 1. So the only thing you can get from Cauchy-Schwarz is that they intersect with probability 1 over log, at least. But if you play the same game here, the first moment of the number of intersection is also logarithmic. Second moment is still logarithmic squared, sorry, so log squared, but the first moment is log. So then Cauchy-Schwarz tells you really you intersect with positive probability. Okay? So we are going to try to use this because this is kind of saying, you see, at least for random walk is saying, then clearly the probability of intersection should go to 0, because if I take 2 points, I have 2 possibilities. Either I intersect, but I do re-intersect at least, say, log L to the epsilon times, but this by just Markov should be small since the expected number of intersection is order 1. Or I intersect, but I do not intersect logarithmically many times, but then just by placing yourself at the intersection, you should manage to have 2 walks starting from basically the same point and not re-intersecting too often. And that will be low probability because in each annulus, so it's not the dyadic annulus, but in each annulus like that, with these growing powers, you should intersect with positive probability. So clearly you don't, this is very difficult for you to intersect. So we are going to reuse the same argument for the currents. And if you want to stop listening, I can basically tell you what are the two things that we will need to check. The first thing is that there is something very specific about the random walk, is that you can condition on the place where you intersect, and by Markov property, then you can place yourself there and look at the probability of intersection. This is not true for currents, but we are lucky. The switching lemma is going to tell us, well, if we want to see that we intersect at a point y, and then say something like, oh, but then we have to intersect many times, then we are going to use the fact that y is connected to x1, x2 to just use the switching lemma to change the sources and get, in some sense, an interpretation where now I am sitting at y and not at x1 or x2, and do the same for the second thing. So we are going to replace the Markov property by the switching lemma. And the second property is that we are going to have, and this is going to be actually the core of the actual theorem, but this I will not really have time to present it today, is we have to prove some kind of mixing. Because here, for random walk, in each annulus, we intersect with positive probability, very good. And then you just say, well, then it's roughly independent. So the probability of not intersecting at all, for instance, is going to be quite small. Proving this for random current is much more challenging because you have a lot of dependencies. These are highly non-Markovian objects. So you have a lot of dependencies between the scales. So you have to, I mean, you don't have, a posteriori you don't have, but you need to prove you don't have, and a priori you could have a lot. Okay. So these are for the two ingredients. So let me try to be a little bit more rigorous on the different steps. So let's define mu of tk or xk. So what is this? These are the set of, so this is a cardinal, the cardinality of k smaller than capital K, such that you have an intersection, xx is non-empty in the annulus around U, which has the following. So now I'm going to take a sequence of scales, L0, L1, etc., L2. And mu xk is for a certain set X. Okay. It's just the number of indexes for which X intersects the annulus. The case. So it's just counting the number of annuli that are intersected by X. Okay. And from this LK, I'm not going to take them completely at random. I'm going to take LK plus 1 to be LK squared. I could actually take here 1 plus C for any number larger than 1 would be fine. But I'm going to take 2. Okay, so let's go back to this quantity that I want to be bounding in a smarter fashion than that. And I'm going to bound this in 2 ways. I'm going to say this is smaller than probability that T is larger than 2 to the delta K. I'm going to tell you what delta is later and what K is later, plus probability that T is like that T has a cardinality which is between 0 and 2 to 0. And my claim is that this, and this is a cool, by the way, it's a cool exercise. I'm claiming that if you take a set which has cardinality smaller than 2 to the delta K, then there must be a point in this set, a U in this set, such that MUTK is smaller than delta K. So I claim that this is the same, it's bounded by the probability that there exists U in ZD such that, I mean, U in T, sorry, so that mu tk is smaller than delta k. So why is that? It's, you want, I mean, imagine you have a set and you know that for this set, so if I take a point in this set, there are many scales around this point that intersect the set. But you know also that in each one of the points, so let's say I know that here this guy, I mean, so the set is intersected L1, but I know that around this point, it's also true that when I look at scales, I have many intersections, right? So because the scales are going super fast, for instance, if you know that the 10th scale is intersected, then the fact that around the point, I mean, one of the points in this scale that is in T, you know you have many other scales, you are going to easily like that construct some kind of counter set of points in your graph T, and you will actually get an exponential number of points. I mean, you see the relation here is not random. You get an exponential number of points thanks to this argument of constructing a counter set. It's a purely combinatorial argument, but it works very well. Actually, it works with delta L, delta K divided by 5 here, but let me, if one of you tried in the plane back home, I don't want him to blame me afterwards. Okay, very good. So when we are here, what do we see? So this, we use Markov. And because this is order 1, it's going to be very small. Okay? And for the second one, here, we are going to say this is smaller than expectation of the number of U's in T such that mu k is smaller than delta k. But the advantage here is that, so here I get 1 over 2, I mean, I get big O of 1 over 2 to the delta k. But for the second here, I can get sum over U of probability of U belongs to T and mu tk smaller than delta k. Okay? Yes.
So k is going to be like log L, right?
Exactly. Yes. Yes.
But then when the first term is small, like 1 over log L, right?
Yes, yes, yes. So you will get 1 over log to some power, which is compatible, right? With they are both comparable. They are both comparable. There, we are going to prove that this is also of order 1 over 2 to the delta k. Both are comparable. I'm going to cut exactly at the right place. I mean, sorry. Actually, you cut at the right place when you said that this should be log log. Then indeed, it's exactly cutting at the right place, and you will get 2 terms of the right order. So here, what does this thing mean? Here, it's something, notice that the mu tk smaller than delta k, by the definition of mu tk, depends only on T. And T is something that is defined in terms of the sums of currents. So if it's defined in terms of the sums of currents, you remember in the switching lemma, there was a functional of n1 plus n2. And this one was not changing when I was switching the sources. It was the same functional. So I can switch the source as long as I'm looking at an observable that depends only on the sum of currents, I can change the 2 things. So here, if I rephrase, maybe let me just rephrase it a little bit different. Here, I'm going to say U belongs to T just means U is connected to X2 in N1 plus N2, and U is connected to X4 to x1 and x2, but that's x1 and x3. This is equivalent in n3% 4. And this is a functional of n1 plus n2 and on n3% 4. So by using twice the switching lemma, once for n1 and n2, once for n3% 4, I can rewrite, so let me forget about the first term. I can rewrite this as probability x1u, x2u. So you see, before I had x1, x2 and empty set, but because I switch the sources, I get these sources. These are for the two first currents. For the two last currents, I get x3u, x4u. And this switching allows me to remove this, and I just get mu tk smaller than delta k. And when I do that, let's be a little bit careful when I do that, because here I have probabilities. I need to be careful about the renormalization constant, and the renormalization constant is exactly like for the switching lemma, for the tree diagram bound, I get this quantity. But this is perfect, because remember that this is exactly what you are multiplying the thing by. So this cancels. So you get exactly the right term here. This is exactly the tree bound, but you improve by this probability. And notice now what is the interpretation of this in terms of path. If we keep in our mind the analogy with random walks. So if you keep the analogy with random walks, now I have four currents. Let's say this is U. So I'm going to write x1, x2, x3, x4. And if I write the two first currents in warm colors, the first current has sources U on x1. So in some sense, there is a forced path from U to x1. The second has a path from U to x2. So together, they form some kind of thing that starts from x1, from U. And if I write in cold colors the two last ones, there is a path from U to x3 and a path from U to x4. So what am I now asking? I'm saying for this thing, is it likely that there are not so many intersections between the warm colors and cold colors? That there are few annuli around me where there are intersections between warm and cold colors. So you see, I mean, here we really turn the question from something where points are in generic position to a situation where we all start from the same place. So what's the only remaining thing to do with a little bit of guillemets, as we say in French, quote mark, is that we need to prove, and this is going to be what we call the clustering intersection bound. Sorry, intersection clustering bound. Yeah, intersection clustering bound. We need to prove that probability 0x1, 0x2, 0x3, 0x4, I'm just translating that U becomes 0, that M0 tk is smaller than delta k. We need to prove that this is small. Let's say e to the minus constant delta. If we do that, if you do that, notice that by plugging k to be log L, we would get a 1 over log L to the C correction. delta C. I mean, this is not the C prime. Okay. At this stage, why did I introduce a delta here? Because exactly like for random walk, what we are going to try to prove is that in each one of the annuli, there is positive probability of intersection. If things were completely independent, then if you take a delta which is which is smaller than this probability of intersection, then it's very unlikely that you will have too few intersections. Okay? And it will be exponentially unlikely in the number of events, which is exactly what we are aiming for. So that's very good. Oh, I don't, sorry. It's e to the minus c delta k, otherwise it's not very complicated to prove. Also notice that here I get log. At no point I get the bubble diagram. At no point I get B. But remember that in our case, it is true that anyway, B is logarithmic. What is going to be the difference when you don't have this assumption that B is logarithmic? The difference is going to come in the definition here of the LK plus 1. We are going to see in a minute why. Actually, maybe I'm going to explain to you a little bit later. Or no, I can tell you now. So it's going to be important when you do the second moment estimate to prove that you have intersection in each scales. It will be important to take scales here that blow up in the bubble diagram. So you are going to define BK plus 1, BLK plus 1 in such a way that it's twice BLK. How many scales will you find? Log BK. That's why this will work here. Log BL. You can find logarithmically many scales in the bubble diagram, in terms of the bubble diagram. Okay, so that's the core. And to be honest, all I did until now, we knew how to do it. We knew this was the way to go. If you look at the random walk analogy, this is what you would like to be doing. This is the hard part of the proof. Okay. So what I'm going to do now is maybe try to justify fairly well, fairly well, it's maybe a big word, but try to justify why you intersect on each scale with positive probability. And then I will state the mixing property, and I'm not sure I will have much time. Maybe I will give you a heuristic why this is true, but I'm not sure I will have time to give you an advanced view on the proof. Okay, so first lemma. The first lemma is going to be if I take X4, then T intersected with the annulus between LK and LK plus 1, so one of the annuli. The probability that there is non-intersection is bounded by a constant C0. And here, maybe you want LK to be much smaller than L. By much smaller, I mean maybe something like LK plus 2. L is a capital. Okay. So this already was something that I think neither Michael nor me noticed for a long time, is that there is a very simple proof of this. Very simple. Of course, you need to be careful just before you present a proof, but okay. So let me try to convince you that you intersect with good probability. The first thing is remember that this is. You want the cluster of N1 plus N2 of 0 now to intersect the cluster of N3 plus N4. Let me drop the 0 because now everybody, it's always a cluster of 0. And you want this intersection to happen in the annulus. This is the estimate you are looking for. And trust me, these clusters, they are bigger if there are more sources. Okay? So I'm going to do a first simplification here. And this is really, I mean, we didn't notice it for a long time, but it's not, once you notice it, it's not difficult. So here, I'm going to remove these sources and put empty sets. Because less sources means smaller sets. So, I mean, they intersect with smaller probability. So if I bound this from below, I'm even better. Why do I do that? Because now I can define, so remember this is, I mean, let's call this guy S. I can define, I can look at the expectation, 0x1 empty set, 0x3 empty set of the set of S, I mean the cardinality of S. And there, notice that this is the sum for U in the annulus of the probability 0x1 empty set of U is connected to 0 in N1 plus N2 times probability, or let me actually all put them together, 0x3 empty set of U connected 0 in N1 plus N2 and U connected to 0 in N3 plus N4. And the advantage here is that these two events are independent. And I exactly know how to estimate them. We did that several times already. U connected to 0, when I have sources 0x1 and empty set, I can switch the source. So this thing is exactly equal. There is not even a correction to the sum for U in the annulus. And with the game of renormalization, I will get the following quantity, sigma 0, sigma U, sigma U, sigma x1, sigma 0, sigma x1, and I get sigma 0, sigma U, sigma U, sigma x3 over sigma 0, sigma x3. Okay, so that's things that we use several times already, and it's in fact the same computation. So it's an equality for the first moment. And notice that this is an equality we can even, I mean, now estimate a little bit better. Notice here, if I want to compare this guy to this guy, how do they compare? Let's look at the position of the points. You have 0, you have your annulus, you have U, and you have x1. Let me put x1. X1 is there, right, in terms of distance. Why? Because I assume that LK plus 2 is smaller than L. So that means that LK plus 1 squared is even smaller than L. And 0, and let's take the case, which is the generic case where 0 and x1 are also at distance. I mean, it's like U and x1 are also at distance of order L. In this regime, you really get that this point is much closer to the origin than to x1. But now, I mean, you will agree with me, it's not then difficult to believe that sigma xu, I mean, sigma u, sigma x1, and sigma 0, sigma x1 in terms of correlation, they are almost the same. Simply because the mutual distance between the two are so between 0 and u is much smaller than between u and x1. In fact, if you assume I mean, we are lucky, we are assuming scale invariance in some sense. This is of order distance between u and x1. This is of order distance between 0 and x1. It's the same order. So this is larger than a certain constant, let's call it C1, sum for u in the annulus. And here I can just kill these two because they are of the same order. And I can play the same game with these two. And what do I get? I get this. And this, if you think about it, it's BLK plus 1 minus BLK. It's the sum of the squares in the annulus. So I have a lower bound on the first moment, which is of order of the bubble, of the difference of the bubble between the two scales. So in particular, even if we are not actually, well, in particular here, because we are assuming that we have the green function estimate for the 2-point function, you get log LK. C1. Okay, let's dive into the second thing we would like to estimate, which is a second moment. If we play the same game, do you agree that what you will end up with is on one side, I will have, so I will sum over U and V. I will have UV connected to 0 in N1 plus N2, and I will have the same estimate, but for 0x3. So this is a little bit more complicated here, because notice that you can switch the sources, say, to make U appear, right? If you do that, these things will become this quantity here times the probability. So let's just one first try. So you switch U and I mean U0. So what will you get? You will get sigma 0 sigma U, sigma U sigma x1, sigma 0 sigma x1. And here I will have the 0 U ux1. But before here we had nothing, so that was giving us exactly that without correction. But now we still have V connected to 0 in N1 plus N2, right? And in some sense, we cannot just bound this by 1, otherwise we would be summing on a void V, so it would be way too big. There will be no constraint on V. So we need to estimate this thing. And this thing, if you think about it, so now you have 0, you have U, you have x1, which is very far, and you are trying to see whether 0 is connected to V, but you see there are force paths. There is a force path from 0 to U, and there is a force path from 0 to x1. So these force paths, they may go through V in a simpler fashion. But if you think random walk, 0 to U, the cost of the red going through V would be sigma 0 sigma V sigma U divided by sigma 0 sigma U, right? And there, that would actually work pretty well, because you will have, if you think random walk, the cost of the red would be, as I said, sigma 0 sigma V sigma U over sigma 0 sigma U. So these two guys would simplify. And of course, there will be also the cost of the blue, but it will be something symmetric in U and x1. Let's ignore this. And what you get here is you get what you would get from random walk, which is, you see here it's saying, you take a random walk in order to intersect U and V. In some sense, it needs to go through V, then from V to U, then from U to x1. Or the other thing will give you, in fact, that you need to go from sigma 0 to sigma V, from sigma V to sigma U to sigma x. So you get an estimate. If you think random walk, you would get an estimate of the following order. You will have UV in annulus. And you will have roughly sigma 0 sigma V sigma U sigma x1 divided by sigma 0 sigma x1. This would be the cost for the red. And again, think that the blue will give you something of the same order. And then for the second guy, you will get also something similar, except of course you go to x3 instead of going to x3. Very good. These two guys here, for the same reason as before, they simplify. These two guys here, for the same reason as before, they simplify, simply because 0 is much closer to U then 2x3 or 2x1. So there, what you would get if you think random walk is sum of a uv, and you will get sigma 0 sigma v squared times sigma v sigma u squared. And now when you do the sum, you sum over v first, over u first. So when you sum over u, you are going to get b 2lk plus 1. You are summing the squares, and the distance between v and u can be as small as 0. That's possible, but it can be as big as 2lk plus 1. And then for the first guy here, if I just sum over v, v is in the annulus, so I get blk plus 1 minus blk. So the first moment, this is something super common, right, in second moment method. You get the first moment, but you get something which a priori is bigger than the first moment. But if you chose, and this is what we did here, if you chose the thing in such a way that this is of the order of this, then you get that this is the square of the first thing. So here, in our case, we indeed get that this is constant, log lk plus 1, but lk plus 1 is just lk squared, so log lk squared. And by Cauchy-Schwarz, I get that there is positive probability of intersection. So, and you see here, I'm not using the log lk. What I'm truly using is that this is of the order of this. And hence the choice in general to take the scale in such a way that the bubble is doubling at each scale. So I lied here because I told you if you think random walk, like in order to estimate this quantity. In fact, it happens that you can indeed see that up to a factor 2, you have the same inequality. In fact, this is really reminiscent from the fact that random currents, there are two ways of looking at them. In certain aspects, when you think clusters and things like that, they really behave like percolation models. When you think links between sources, they really behave like self-avoiding walks, like repulsive walks. So if you have an estimate for random walk of the type, like I'm bounding by certain probabilities, then in general, this will actually be even more true for random currents. So the game is to manage to walk on a thin rope where you basically need to be on the side of the random walk interpretation when you want to be bounding from above by things like self-avoiding walk. On the self-avoiding walk when you want to be bounding in things a little bit a la random walk. And when you want like correlation inequalities and maybe positive association, you want to be on contrary on the side of the percolation interpretation. And it's not that easy to juggle between the two, unfortunately. We would like it to be more straightforward because that would be even more powerful and maybe a little bit less technical. But in fact, this juggling is not so easy. So bottom line, this bound is actually a bound on this probability, up to the fact that I didn't wrote the symmetric thing with you. Okay. So that was for, so this is saying, in some sense, I could have called it the intersection property. Indeed, you intersect in each annulus. So now let's dive into the last, let me give you in the last 10 minutes a small idea of the mixing bound, because we need also a mixing. Okay, and the mixing property is going to say the following. Let me try to. So imagine you take an event that depends on the inside of your annulus. So let's say call it A. And an event B that depends on the outside. And you put some space in between, like you put one full annulus in between. This is not super moral, but it's just you want to have a certain distance to be able to decorrelate. Then I claim that the probability, so say fix x1. So there's going to be even one current only. So x, which is not in lambda L k, plus 2, say something like that. And let's say A be depending on edges in lambda LK, and B on edges outside LK plus 1. Okay. So A is depending on those edges, B on the edges outside. So what I claim is that when I'm measuring the difference between the probability of the intersection and the product of the probabilities, I get something small. And the something small is log LK. Some power. And that basically, because it's true for one current, then by applying to 4 currents, you also get a mixing. In fact, you can directly state it in the 4 current context. And then combined with that, it will tell you that it's very unlikely not to have the right density of scales on which you intersect. So the only thing I will do in the last 5 minutes is to just make you feel that this is not so easy, and there is something a little bit miraculous with the fact that we managed to pull out the. So, in order to show that this is a little bit difficult, let me make an analogy. Imagine you will not have sources. So, replace 0x by empty set. Okay. So you look at mixing when you have sourceless current. What happens is the following. So you have what happens in A, and what happens in the NLS, and what happens outside. If you don't force the existence of sources, you are at criticality. This is true for any. Let's take beta equal beta C, sorry, because actually it's wrong. We are, I'm sorry, I forgot about that. We are at beta C. No? So in this case, if you don't have sources, what happens at beta C? You know that at beta C, you have a continuous phase transition. So really think the random current doesn't lack to have long clusters. It doesn't have an infinite one in particular. And what happens here is that there is not going to be, typically, there will be 0 cluster crossing like that. It's just two, it's a cost which is way worse than this. It's actually polynomially small. And in some sense, the only way you impact from the inside of the, what happens here impacts what happens here is through the shape of the boundary. So you measure all the clusters touching the boundary here. You measure all the clusters touching the boundary here. So only the shape of the boundary here is impacting what happens outside. And it's just impossible to find weird events here that are going to make that the shape is so strange that it's going to impact what happens outside. In particular, the only way the shape could impact is if indeed there would be large clusters coming. This is something that is, for instance, very easy to prove if you assume continuity of the phase transition for percolation, say. Then the only way for Bernoulli percolation, the only way you impact is if there is a path. If there is no path, then things are independent, just purely independent. So if you assume continuity of the phase transition, you can expect that it's very unlikely to have a path from the inside to the outside, and you are done. Okay, but that's not what we are doing, right? What we are doing is that we are forcing sources, 0 and x. And let me give you an example where things go bad. Assume that you are at, so this was the first thing, so there is no problem. It was the bottom line of what I want to say. So now assume that you have 0x as sources, but that beta is smaller than beta c strictly. Okay? And take a very, very large scale, a scale much larger than the correlation length of your system. You have exponential decay of correlations, and you take scales that are much larger. This is something you may know if you take a subcritical system and you force the existence of a path between 2 points. The exponential decay is going to make it that the shape of this path is going to be a Brownian bridge between the 2 points. So here, what happens, or if you want a massive random walk forced to go to the second point. So what happens here is that up to diffusive fluctuations, the point is going to go straight from 0 to x. But now it's clear that you can cook up some bad events that are going to be very correlated. Imagine you take an event here or here, like crossings. The crossings are going to be very correlated. In particular, if you force an event, maybe if you say, I want a crossing here, let me rather write it like that. This is forcing something catastrophic on the path, and it's going to tilt it in such a way that now its behavior is going to go like that. Okay. So in this regime, you can do crazy things. There is no mixing a priori. There is maybe an additive one, I should say, but let's not bother on that. So the bottom line of this example is that, in fact, once you have sources, it's very likely that the path itself can carry information from inside to outside. So you need to prove this is not the case. And yeah, I don't have time to do it, but in order to, I mean, the trick is a little bit funny. The trick is to kind of condition on, let's say, condition on the fact that the path between 0 and x goes through a vertex u in the middle. And the switching lemma in this case tells you something super cool. It tells you if you add a second sourceless current, it tells you that then it's a little bit like in the first current, you are forcing a source from 0 to u, and in the second, a source from u to a path from u to x. So now, if in the switching lemma you do things smartly, what you are going to manage to do is that the event A is going to only depend on the first current, and you are going to switch the event B. So before we had only one current, right? So you start with one current, you add a second current. If you do the switching smartly, you can switch the event B to the second current. And then things decorrelate because they are not in the same current. So, I mean, I'm well aware that this is not a very convincing explanation. It's not a very simple argument. But really, the trick is to decorrelate by introducing, I mean, by looking, if you want, at the point in the middle that this path that may carry information passes through. And by doing that, you manage to decorrelate and to make the event A and B lie on different clusters, on different currents, and you get independence out of that. So it's a fairly surprising argument, I should say. It's a little bit, I mean, maybe I should tell you where the log comes from here. It's going to come from the fact that in general, you don't want to be conditioning on a point in the middle. Too much. I mean, why would 0 go through a given point? So what we do is that we introduce a random variable, which is a weighted sum on indicator that you intersect the point, that you go through the point, sorry. And the whole goal is to prove that this weighted sum is an approximation of unity. It's basically equal to 1. And how well it is close to 1 is related to this term. Just let me mention that this switching somehow tells you in particular, you see, by letting B events on, in fact, the whole thing go to infinity, it tells you that you can construct the current, the random currents, condition on having a source at 0. The infinite random current condition to have a source at 0. Just to make an analogy for people who know about this problem, in particular, we are in high dimensional geometry workshop. For percolation, there is a similar question. take critical percolation, can you construct the measure where 0 is conditioned to be connected to infinity? It's a famous incipient infinite cluster. It is constructed in high dimension. It's very difficult to construct in small dimensions. This thing tells you that for the random current, which is a much worse percolation model, you can do it. So there is something very mysterious about this random current that on some aspects, it's much simpler than percolation, and on some other, it's really, really worse. So the game is to always lie in the part of space where it's simpler. Thank you very much for your attention and for attending the 5 lectures.
Yeah, I have very naive questions. So this mixing lemma is true for beta less than beta C also?
Yeah, I mean, with additive, it is true. I mean, that's why when I was writing that, explaining this, I was like, oh, yeah, what am I doing? I think so for beta smaller than beta C, what is certainly true is that it's true in the same way as that criticality up to the correlation length. Above it, one has to think about exactly what you will get because these are still condition measures. No, I mean, so my argument here, sorry, is a counterexample for beta smaller than beta C when you are above the correlation length.
Okay.
Just because you start to have this this Brownian scaling.
I see. And can you just remind me what happens in dimension 3? So marginal triviality is not expected.
So in dimension 3, that's a very good question. This is perfectly true. In fact, we don't use dimension 4 there. So you have mixing. And that the problem is that the intersection property, like you don't even need to take like strange shapes. You actually intersect typically even in dyadic scales. But that means, so this is fine. Like if you intersect, you reintersect many times. But in fact, just the expected number of intersections to start with is very large. Here we use the fact that to start with, we have big O of 1 expected number of intersections, and we improve on it. But in dimension 3, in fact, this path, they don't look like random walk. They really think the analogy is they would look a little bit like you would expect maybe from, I mean, it's not in the same universality class, but think self-forwarding walk in 3 dimensions. They don't look like random walk at all. They feel the repulsion. Here it's the same for these currents. The scaling is not going to be the one of random walk, so the analogy to random walk is just wrong. So there, they reintersect, and in fact, you expect the probability of intersection for 2 generic random current to be positive. There is a paper, I gave the reference. There is a paper by Slava Ryzhkov and co-authors in physics that estimates U4 in dimension 4 numerically. In dimension 3 numerically, and they get a number between 0 and -2/3, something like that, which are the trivial bounds you can get, and it's not tending to 0.
So what is expected in dimension 3 to happen?
So that means it's non-trivial, it's non-Gaussian. Now the scaling limit, they don't know, even using conformal invariance, even assuming conformal invariance, they don't know how to describe the scaling limit. And it's not the same thing as 543 type of, for people who have the analogy with 543. It would be actually the scaling limit we are talking about would be to take the scaling limit for critical 543. So it's yet one more step of taking the limit. And there we don't know. Even with conformal invariance, we don't know. We don't know how to identify the critical exponents. So all this conformal bootstrap field that is blossoming in physics, it's about estimating the critical exponents using conformal invariance in 3D. In 2D, you get immediately the exponents. In 3D, it's not sufficiently strong to exactly get the exponents, but they manage really to get amazingly small areas of space where these exponents can lie. But it's not entirely clear whether it's determining the critical exponents a priori. Like, of course, this is based on numerics and things like that. So it's partial information in some sense. So you could imagine that if you had an infinitely strong computer, in some sense, maybe you could actually determine the critical exponent. It's not very clear. So even the critical exponent, which is somehow maybe a little bit simpler, they don't know how. So it's mysterious. We still have some work for the 21st century.
Okay, thank you.
Any other questions? All right, if not, let's thank Hugo again for this wonderful set of lectures. I'd like to thank all the speakers for the last 2 weeks also.
Sorry, we should thank the organizers. Sorry, I'm never the last speaker, so I forgot this. So thank you very much for this wonderful workshop that we all enjoyed, and the invitation here. It's a splendid institute, and I think we all will enjoy it. Thank you very much.
Yeah, thanks. Thanks everyone for coming.